In this video, we learned the basic derivative rules and the rules for basic differentiation. So some of the ways that we were able to take derivatives with the limit definition, if we remember here, that limit as h approaches 0 of the difference quotient, we had to go through all the limit processes that we learned in chapter 2. And that just became very cumbersome and time-consuming. But of course, there are nice, quick ways around using that limit definition, and I'm going to allude kind of throughout the whole video that all of the rules that we're going to learn here today are a product of that limit definition. So they don't just come out of nowhere, right? They can all be proven with the limit definition, okay? The first thing I want to explore here is what we call the constant rule. Right? A lot of these have names: constant rule, constant multiple rule, power rule. And some of them you'll remember the names of, and some of you won't, and that's okay. But just kind of getting the basic ideas here. Say I want to take the derivative of some function f of x equals k. I would take the limit as h approaches 0 of f of x plus h, or k, minus f of x. So f of x plus h and f of x are the same here because my function is constant for any x. And we can see quickly that that limit is exactly just going to be 0. So we can say that the derivative of any constant is always 0. Now with all derivatives, this should make sense in the context of the rate of change. And the rate of change, and also then the slope of the tangent line. So what I should be able to extract from this is that the slope at any point on f of x equals k is going to be 0. If I draw some constant function here, no matter where I'm at, x or x plus h, I've got a slope of 0. Right? So this constant rule tells me that no matter what, if I'm taking the derivative of a constant, the slope of a constant function is always 0. Right? Easy enough. And again, it comes from the limit definition. I want you to consider this basic linear function, y equals x. It's the most basic linear function that we can think of. And I want to find the slope of the tangent line, or the derivative. What's the derivative to this function? Well, if we think about it in the context of slope, what is the slope of the tangent line at any point? These two things are asking really the same question. It's worded differently, but the result is the same. And I want to then think about this function in the context of slope-intercept form, mx plus b. Y equals x can be written as 1 times x plus 0, in which case I can see the slope, my m, is just going to be 1. The slope of y equals x is 1 for any x. So that means the derivative of my function is 1 for any x. Okay? Or d dx of x is just 1. Okay? And this is going to hold for all linear functions, this idea where the slope is the same for any x. That's true for any linear function with a slope, say, m. So the derivative of anything like m times x is just going to be m, the slope, okay? All these kind of two ideas here, along with the constant rule, can be described with what we call the power rule, okay? So this is going to handle any function that has x to a power. The derivative of x to some power n, where n is, we say, rational, where n's a rational number, is just n times x to the n minus 1. Okay? We have the original power of the function. We bring it down in front as a multiple, and we raise that x then to not n anymore, but 1 less power. Okay? Well, I'm going to do a bunch of examples here where I use this power rule and kind of make sure we get a feel of how it works. Again, this can be proven with the limit definition. It's just a little bit difficult to prove, so I'm going to omit that. If you're interested, you can, of course, look up the proof of the power rule. For example, let's look at the derivative of x cubed. Okay, my exponent here is n. My exponent is 3, and that's going to be brought down in front. And then I'm going to take x and subtract 1 from the power. So instead of a power of 3, I'm going to have a power now of 2. My derivative would be 3x squared. That's it. I could show this through the limit definition. I could take the limit as h goes to 0 of x plus h quantity cubed minus x cubed all over h and work through the expansion of that and simplify it, and you would end up with 3x squared. Okay. Another example, the derivative of the cubed root of x. Okay. For this, we have to remember that a radical there, that cubed root, can be written as a fractional exponent, x to the 1/3. So there's my n, my power, and I just bring that power down in front when I take a derivative, and I subtract 1 from the power. 1/3 minus 1 is a minus 2/3. Okay, so we are allowed to have negative exponents. That's fine, nothing wrong with that. We often rewrite them. That negative exponent I can think about as being positive as long as the x is then brought down to the denominator, or what's being raised to that negative 2/3. And the 2/3 power can also be written as a radical. So these are all equal, right? All my equal signs there. Those are all technically correct. And depending on what we're doing, if we're actually finding the slope of the tangent line or doing something else with this derivative, we'll work on some of that later, then we might want to write it in one format over the other. Some of these formats have better use, I guess. But there's my derivative. Regular, pretty simple, straightforward power rule. Let's do another. If I have a function, f of x equals 1 over x squared, and I want the derivative. I need to write that with a exponent, just one exponent, x to the power, and that power is going to be minus 2. So my derivative, I'm just using slightly different notation here. Instead of my ddx notation, I'm using my function notation, f of x. So that means that f prime, the derivative, will be my power brought down, negative 2, and subtract 1 from the power, x to the minus 2, then minus 1. So minus 2 minus 1 should give me a minus 3, and I'm just going to then quickly bring that down to the denominator. So the power is now minus 3, and I bring that down. Okay, so what we realize here is that if our power is negative and we're taking a derivative, we're going to keep getting negative powers. We shouldn't somehow end up with positive powers of x anymore. We should just kind of continue to have negative powers as long as we're taking derivatives. Okay. Not power rule would be something like 3 to the x or e to the x. So these are exponential functions. They have a base that's a number. E is a number, yes, seems like a variable, but they have a base that's a number and an exponent that's a variable. These do not fall under what we would call power rule. Okay, so we'll learn how to take a derivative of either of those exponential functions a little later. But for now, let's look at finding the slope of the tangent line of f of x equals x to the 4th at x equals minus 2. So this is a derivative question, right? Find the slope of the tangent line. And to do that, I need the derivative, right? If my function is x to the 4th, then my derivative, really what I need is my derivative evaluated at negative 2, right? That's going to give me the slope at negative 2. So I take a derivative here, bring the 4 down, subtract 1 from the power, I get a 4x cubed. So then plugging in negative 2 to that is going to give me a 4 times negative 2 cubed, or 4 times negative 8, which is a negative 32. That's my slope. What if I want the equation of the tangent line instead of just the slope? I want the slope, but also I want the line that has the slope and that passes and kind of touches my function when x equals minus 2. Well, all I need then is just another point on my graph. I need negative 2, f of negative 2. I need that point in particular. So I then plug in negative 2 to my original function, right, to find the y value. This f of negative 2 is on my function. So I plug that in. I get negative 2 to the 4th power. That should be a 16. And I'm going to use that point then, negative 2, 16, to figure out what the equation of the line is that passes through that point with the slope of negative 32. I use my point slope form here. Y minus 16 is equal to the slope, m, negative 32, times x minus x1, or x minus a negative 2. just simplify this a little bit. If I put it then in slope-intercept form, which is easier to graph, I have y equals negative 32x minus a 48. So just another exercise that's completely derivative based, where we're looking at the slope of the tangent line at a point of a function and then the equation of the tangent line. So a pretty typical question type, typical thing that we're interested in with this now new knowledge of derivatives. There's a couple more rules we have to see here. The first is a constant multiple rule. Okay, so for example, if I have the derivative of a constant times some function of x, where k is a constant. Okay, it's just some number, and f we know has to be differentiable. Okay, otherwise I can't take the derivative, right? But all that's going on here is that this k is scaling, right? It's either stretching or shrinking depending on the value of k. It's stretching or shrinking my function of x, and that has an effect on the slope. And the effect on the slope of the function is exactly that stretch or shrink k. So this should be then k times the derivative of my function, right? This is really beneficial for us because now we can handle anything that has a constant in front of it. For example, the derivative of 5x cubed. That 5 is a constant multiple. We can bring it out and take the derivative then of just my x cubed, which we know now to be 3x squared. Multiply the 5 and we get 15x squared. Right? Pretty straightforward. Once you do a couple of these, you'll end up kind of foregoing pulling this 5 out and end up being able to just multiply there. Let's do another one. 2 over x is my function I'm working with. Y equals 2 over x. And to be able to take a derivative, I first need to see that x has a power of minus 1. The 2 doesn't have that power, just the x, and that's important. So my constant multiple here is 2. When I take a derivative, that 2 is going to be multiplied by the derivative of x to the minus 1. And for that, I bring the negative 1 down and subtract 1 from the power, negative 1 x to the minus 2. Same power rule, we just have constants now that are kind of in our way. It's tempting to say that the derivative of those constants is 0. If you didn't think about that, no big deal, good. They fall under our constant multiple rule. There are constant times a function. The slope should still be something, right? It shouldn't just be 0. And that constant scales our slope, right? So that's still involved. This derivative would be like a negative 2 over x squared. And the reason I do an example like that is because it's often confused with something like this. Derivative of 1 over 2x. Okay, so notice the difference. Before, the 2 was in the numerator, now it's in the denominator. And that does matter. But I'm taking a derivative with respect to x, and that 2 isn't necessarily tied to the x like we expect it to be. I can factor out what we have here as a 1/2 now, and take the derivative of x to the minus 1, again, the same as I did in the last little example. Okay, so subtle difference here, but we treat that 2 in the denominator as a constant 1/2, right? I could rewrite that as 1/2 times 1 over x and take the derivative to get me a 1/2 times minus 1 x to the minus 2, or minus 1 over 2x squared. Okay, so I write that 2 back down in the denominator and it feels like it's part of x squared, but again, it's not. It's multiplying x squared. Okay, so some subtle differences. Another one here, changing variables on you. Derivative with respect to t now, d dt, of 4t to the 3/2 divided by 5. Okay, we handle this pretty much like we did the last one. Since the power of t is already there and already positive, I don't really have to move it anywhere. I don't have to rewrite it. I would just take this 4/5 outside of my derivative. So my power then is brought down to the 3/2, and I subtract 1 from the power. 3/2 minus 1 is a 1/2. And I do have some simplification here. I can divide 2 into 4 to have a 2 left over. 2 and 3 is 6. And t to the 1/2 is written typically as the square root of t. Okay? So we've got some basic power rule going on here, and I've tried to accent some different types of powers, fractional powers, negative powers, things like that. and all along with some constants, constant multiples that we have to kind of leave that just come along for the ride, is what I typically say. So that they're there, we just kind of leave them there and we work around them, and they are going to multiply everything. Okay. The second rule that we have to learn here is sum and difference rules. Okay? These are really pretty straightforward, but a little background here. If f and g are differentiable, then we can say that the derivative of f of x plus or minus g of x is equal to the sum or difference of the derivatives, f prime of x plus or minus g prime of x. Okay? So I use plus or minus here to kind of handle both rules at once. Right? In practice, this is a lot easier than it looks. This proof also comes from the limit definition, right? So I'm able to show this with that difference quotient in the limit definition. This one's actually relatively easy. I just didn't want to take the time to do it in this video. But you're welcome to explore that if you are interested. Now we can handle the derivative of any polynomial, any string of constants times powers of x, we can take the derivative of. So for example, a cubic function here, x cubed minus 4x plus 5. When I take my derivative, I take the derivative of each term separately, and they're strung together by the pluses and minuses that are already between the terms. So my derivative would be the derivative of x cubed minus the derivative of 4x plus the derivative of 5. And again, those pluses and minuses come right from where the pluses and minuses are in my original function, what I'm taking the derivative of, okay? And I just handle each of them separately. Derivative of x cubed is 3x squared. Derivative of 4x is 4. And the derivative of 5 is 0. So I've got 3x squared minus 4 as my derivative. That's it. Again, when we take a derivative of a polynomial, the highest power should be 1 less, right? So I went from a cubic down to a quadratic, right? That's always going to happen. Always, always. Similar, y is equal to minus x to the fourth over 2 plus 3x squared minus square root of x. There's a square root function again. I'm going to want to write that as a power, but when we take the derivative of these sums or differences, right, we treat each piece separate. So I've got minus a half times the derivative of x to the fourth. Derivative of x to the fourth, so this is 4x cubed, plus 3 times the derivative of x squared. That one I bring the 2 down. 3 times 2 is a 6x, and that should just be x to the first. Minus the derivative of square root of x, so that's minus the derivative of x to the 1/2 is 1/2 x to the minus 1/2. I'm going to just quickly rewrite things here, and I see that I've got negative 1/2 times 4 is a negative 2x cubed plus 6, that should be an x, minus 1 over 2 square root of x, right? That x to the minus 1/2 I can bring back down into the denominator, not back down, but bring down into the denominator and write with a positive 1/2 power, which we often write as the square root. Okay? So I can handle any polynomial with my sum and difference rule, my power rule, and my constant multiple rule. Okay? Every once in a while, you'll have a derivative that is 0, right? The derivative with respect to x of 5 there, that constant was 0. Just have to remember that as we go along. So I handle things piece by piece across addition and subtraction. Multiplication and division are different. We have to be careful with those. We'll learn that in the next section. Okay? A few more things. Derivatives of sine, cosine, and exponentials. Well, not quite all exponentials just yet. We're just going to handle the natural exponential, the natural number e, derivative of e to the x here. So what I want to look at is the derivatives of sine, cosine, and e to the x. Okay? Again, these are all proven with our limit definition. But what we get here, derivative of sine of x is going to be cosine of x. We would love for the derivative of cosine of x to be sine of x, but it's not quite. It's minus sine of x. And wildly enough, derivative of e to the x is just e to the x. It's itself. The slope of the tangent line at any point along the curve e to the x is e to that power. That's wild. It's very cool. We'll talk about that more in a later section. Okay? So these are our derivatives. And again, these are all from the limit definition. Okay, and you can explore those if you like. They're somewhat difficult to do, but you can find proofs online pretty much anywhere. Let's do some examples. Derivative of 2 sine x. If I have a function that's 2 times sine, the derivative f prime is just 2 times the derivative of sine is 2 cosine. Easy enough. Constant multiple rule at play there, but no power rule, right? No power rule with these guys. It's just they have their own special derivatives, and we have to honor those. Y equals x to the minus 1 plus cosine x all over 2. Okay, so all of my cosine function there is divided by 2. I can handle x to the minus 1, no problem. That should be a minus 1 x to the minus 2. But the cosine x over 2, that's the same thing as 1/2 times cosine of x. So I really write that 1/2 out front. Derivative of cosine x is minus sine x. So we simplify that to be minus 1 over x squared minus sine x, and we can write that as minus sine x over 2 or minus 1/2 sine x. Either or is fine. So some basic rules, some sum and difference rules as well there. Let's bring in e here, derivative of x squared plus e to the x. X squared plus e to the x, derivative of x squared is 2x, plus the derivative of e to the x is just e to the x. It's actually kind of difficult because of how easy it is. Right? We're expecting to have to do something here, and like I said, we'll explore that derivative a little bit more later in a few later videos. Another example, sine x minus e to the x. Nothing too crazy going on. I could add constant multiples. I could multiply things by negatives, but really we all handle it pretty much the same way. Derivative of sine is cosine x, and minus the derivative of e to the x is e to the x. Okay. So here's the most basic derivative rules that we can write down, all of them stemming from the limit definition. We're able to find all these patterns and handle things kind of with these, what I call shortcuts or basic derivative rules. I suggest doing lots and lots of examples for these kind of things. The better that you understand the basic derivative rules, the easier the rest of the semester and the rest of your journey through mathematics will be. Okay, so we'll handle some other functions. Of course, there's more functions. We didn't talk about the other 4 trig functions. We didn't talk about logarithmic functions. Those all have derivatives as well, and we'll explore them in later videos. The next video will talk about rates of change. Thanks for watching.